Good morning, ladies and gentlemen. Now, on the Scifest greeting scale, that rates about a 5. Good morning, ladies and gentlemen. Definitely a 9.5. Thank you very much. My name is Stephen Ashworth, and I'm here from the University of East Anglia in the UK. And I've been asked to tell you about some chemistry. Now, I trained as a chemist. I teach chemistry at university. And of course, I think chemistry is important. But I think you would also agree that chemistry is important because if you think about it, you're made up of chemicals. You eat chemicals. You breathe chemicals, you wear chemicals, we build with chemicals, so everything is chemicals. And if you ever see a label on a product that says chemical free, it's a lie, because everything is chemicals. In fact, there's a joke, it's a rather bad joke, but there is a joke. Why should you never trust an atom? Because they make up everything. But now, what a chemist wants to do is to be able to control the world around them. The chemist wants to be able to know what's going to happen if they mix two things together. They want to know how fast it's going to go, whether heat is evolved, whether color change is going to happen. They need to know this. And so we're going to see some of that today, I hope. Now, if you've seen a previous incarnation of kitchen chemistry, you might think, oh, we're going to see the same show again. Well, it's all different. So this is something new for everyone here. But, of course, if you go into the kitchen, you're going to do some chemistry. It's called cooking. And if you're in the kitchen, do you wear any protective clothing? No? I don't want to do your washing then. You get grease splatters on your clothes and you spill stuff down. Well, at least I do when I'm in the kitchen. So, do you wear anything to protect you? Yes. What do you wear? An apron. So, let's get my chemistry apron here. Now, my apron happens to be a white coat, but it doesn't have chemist. Not. Oh dear, I'm losing my marbles. Thank you very much. Not all chemists wear white coats. You might do chemistry at the bottom of the ocean where you're wearing a wetsuit. You might do chemistry in space where you have to wear some sort of spacesuit. You might do chemistry at a volcano where you're wearing a heat protective suit. So there are all sorts of protective suits you might have to wear that are not a white coat. What else would I need if I were in the kitchen? Gloves. Goggles. You wear goggles in the kitchen? Now, that's actually a good idea. It's not such a bad idea to wear goggles in the kitchen. We don't tend to do that. But I'm going to wear safety specs today. And actually, these are a bit dusty from yesterday. But gloves. You might use gloves to protect your hands from heat. Now, in a chemistry lab, what you do is you look at all the chemicals you're going to use, and you say to yourself, what gloves do I need? How do I need to protect myself best? Do I need a face mask instead of just the goggles? And I've looked at all the chemicals I'm going to use directly, and I've said to myself, oh, actually, I don't need gloves. So I'm not going to wear gloves today. But I said that chemists like to control the world around them. And I want to do a little test to see how well your powers of control are working today. Now, I have a bottle here. And you might be able to see that there is a stream of water coming out of the bottom. Can you all see that? Well, look harder at the back. Now, what I want you to do is try and deflect that stream of water. So either make it bend one way or the other. You can use the power of your minds to do it. Concentrate really hard. Nothing's happening. Okay. Oh, I know. I know the problem. This half of the room is pulling that way, and this half of the room is pulling that way. And so as you both pull in opposite directions, it sort of balances out. and doesn't go anywhere. Is that right? Okay, well, let's try it. Let's try you pull that way, and you try and push that way, so you deflect it in that direction. Can we do that? You can start. No, okay. That's not working. What we obviously need is a little magic. And so I have the thing to make magic, my magic wand, and what I need to do is take my stockings and charge this magic wand up. And now we can see what my magic wand does to the stream of water. Do it this way as well. So I'm not touching the stream of water with that magic wand, but nevertheless, I'm able to deflect it. So, what's going on there, you're saying to yourselves? What? Obviously not. Oh, that's okay. I'll go on to the next. No, oh, right. Well, the thing is, water looks like this. This is a photograph that I took of water earlier and had printed out. You do know how to take photos like this, don't you? Good. So water looks like this. It's got two H's and an O. H2O. That's why we write the formula for water is H2O. There are these two sort of bunny ears and O there. But you will agree that this end looks different from this end, doesn't it? So what happens in water is that this end is a little negative, and this end is a little positive. And because my rod, I could charge that up with some static electricity. So I had static on the rod. The positive and the negative were attracted and repelled from that, and that deflected the water stream for me. Now, this property of water has some consequences. For example, it means that oil, which is here, and water, which is here, they don't mix. That's because these oil molecules, they don't have the positive bit here and the negative bit there. They're all the same all the way along. So that's why this oil doesn't like mixing, or it's not favorable for the oil to mix with the water. It wants to stay separate. But this becomes a problem when you do go into the kitchen and you have done your kitchen chemistry and you've done your cooking. It becomes a problem because you want to do the dishes, you want to do the washing up and mix this stuff with this stuff. So how do we do that? We use dish soap. And your Sunlight liquid, although other brands are available, your Sunlight liquid looks like this. Now this end, this little head here, has a charge. And it's very favorable for water to gather around that. This end here looks just like one of those fat molecules. It doesn't have any positives and negatives and pluses and minuses. And it's very unfavorable for water molecules to gather around that. So this doesn't want to mix with water, but this does. Now, do you want to learn some long words? Want to learn some long words? Okay. So this end is water-loving. We call it hydro, that's to do with water, hydrophilic, because it loves water. This is water-hating. What do you think that's called? Hydrophobic, exactly. So that is hydrophobic, and that is hydrophilic. What I'd like you to imagine is that I have here my washing up bowl. There's the water, there's the air, and this is the surface of the water. So when I start adding my dishwashing liquid, what happens is this. You see those tails are hydrophobic, They get as far away from the water as they can, but the heads are hydrophilic. They like being there nice and stable, dunked in the water. It's favourable for them to be inside the water. And so I keep adding dishwashing soap until the surface is absolutely full, jam-packed with these. Then I add some more. What's going to happen then? Well, this forms. And this is called a micelle. So you see all those hydrophilic things are on the outside. They like being in contact with water. All the hydrophobic things are on the inside. They don't like being in contact with water. And they have been protected by this shell. So you've got to imagine this is like a ball now with all these on the outside and all this on the inside. Along comes your fat molecule that you're trying to wash up and get off your plates. This is your fat molecule. That can now dissolve quite happily in the fatty bit here and gets locked away from the water so we can wash it down the drain. But this also has a consequence because it allows us to make very, very, very thin layers of water. If you now imagine that this is a very thin layer of water, what I can do is have these on one side and some more on the other side. And that makes our soap bubble. And so I've got a secret recipe soap solution here, available to anyone who has an internet connection. And what I'm going to try to do is make a bubble. So what that is a very thin layer of water with these dish soap molecules either side, sticking out inside and outside of that bubble. Now you'll find lots and lots of different recipes for this mixture on the internet, and it's just a matter of a little experimentation with your local conditions and your local brands of detergent to find the best mixture. But why stop with a circular bubble? What I'm going to try to do is make a bubble shaped like a pyramid. And if we are lucky, no, it didn't work. Now they say don't work with children and animals. There we are. The one in the middle is shaped like a pyramid. Actually, I've got two in there. So I've just made a little frame. There's wire at the bottom, and the rest of it is string. But why stop with a pyramidal bubble? Why not try and go the whole hog and make a square one? Again, I've got to try and get this all wet in my bubble solution. The only trouble with this is my hands go all slimy now. So oh, no. Nearly there. Try again. Oh dear. It's a very good day for bubbles today because the atmosphere outside is nice and humid, and high humidity helps in bubble making. Let's just, okay, I need to dip it again to make my square bubble. Oh, it's not. No. One more try, and then I'll give up. But you can see there is a sort of square shape in the middle, but I'm trying to get a cube made. No. Nearly, but not quite. We saw the triangular one, and we saw some nice round ones. Thank you very much. Thank you very much. Now, this property of water with a bit of positive on one end and a bit of negative on the other might lead you to think, well, surely water can conduct electricity. So let's have a look at that I have a little device here. You might be able to see it's got a ring here and a ring here. Now these are two pieces of copper. And if you look here, I have a black column, and you'll be able to see some lights light up. So what I'm going to do is connect these two with a piece of metal, and you see all the lights light up. Can you see that? Now that's telling me that electricity is flowing between these two. Here I have some water. Now this is very pure water, and what we can do is see whether electricity flows when I put this in here, and oh. So what that is telling us, that if we have water and absolutely nothing else, that electricity won't flow. So that's very pure water. Let's try a sample of water out of the tap. What do we see there? So that is obviously telling us that the sample of water out of the tap hasn't just got water in it. There must be something else in there, something that's dissolved in the water. So let's try and add some more stuff that dissolves in water. I've got here glucose powder. It's a sort of, you can use sugar for this if you want to do it at home. But glucose powder dissolves particularly easily, so I'm going to add some glucose powder and see if any more lights light up. So is it sufficient just to dissolve something new in here? No, not really. That glucose powder dissolves in water nicely because it's got the positive somewhere and the negative somewhere else. It's not all the same like our fat molecules, but it's still not conducting electricity. What do we have to do to make water conduct electricity? Well, if I add some salt, what happens? So now you see that indeed that water is conducting electricity, and so that tells me that salt, when I dissolve salt in water, something changes and it can now conduct electricity. So let's think about salt. What does salt look like? Well, it looks like this. This is another one of my famous photographs. Salt is sodium chloride. So if you think of this yellow ball as a sodium ion, it's not an atom anymore, it's an ion because that's got a charge. That's got a positive charge, and this chloride ion has got a negative charge. And you've got to imagine that there's this big crystal with these going out in all directions. There'll be a green one here, and then a yellow one there, a chloride and a sodium ion, and then behind here there's another one, a chloride and a sodium ion, and going out that way, and going out, and going out. All over the place. Then there are septillions of these things in a few grams of salt. But what happens when we dissolve this is that structure breaks apart. It falls apart, and so if this ion is now all on its own. This is a sodium ion, so if you remember, that's positively charged, and so what water does is cluster around it like this, clusters around it like this, and you've got to imagine another water at the front here and another one behind, and that allows the crystal to dissolve. Oh dear, I've wet the floor here. That allows the crystal to dissolve, and now this ion can move. When we try to pass electric current through it, this ion can move this way, and then the chloride ion, which is carrying negative charge, that moves in that direction, and so that allows current to flow, which tells me that if I find a bag of salty water, I can pass current through it. Now the beauty of this is that I am looking out on an auditorium full of bags of salty water. So who would like to join me on stage and have an electric current pass through them? So 1, 2, 3, 4. 5, 6, 7, 8. All come up here, please. So what I'd like you to do is form a line from here. So if you'd like to stand there, you come closer, come closer. Okay, you need to stand here, 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 and here. Right. Now, can you hold that for me, please? Can you hold it tight? Wonderful. You trying to get on the end or get off the end? You know what's going to happen, do you? You need to hold it like that. Right. Now, this won't hurt too much. If you feel that getting hot, just drop it. Okay. And what I'd like the audience to do, if you could just watch their eyes to see if they light up. So I'm now going to connect. Now what I need you to do, everybody, is hold hands. Right, well that's the sound of the machine warming up. That's the sound of the machine warming up, and we should Now what I want you two to do, no one else do this, but you two, if you just break contact now, stop holding it. Oh. What's gone wrong? Let's try another tune. Yes, something was meant to happen. I don't know what. But I've now... Oh, there we go. Let's try this one instead. So are we all holding hands? Oh, no. Let's try this one. Right, now try it. And back again. And if you break... What? Hold hands, hold hands. And if you break it here, stop holding hands. Now, do you feel a tingling sensation? No? We can turn up the voltage next time. No, keep going, keep playing, keep playing. Just remember to turn the dial up. Hold hands, hold hands. There we are. So, every time you break it, the music will stop. Yep, and again. So what they're making here is a connection, because each of them is this bag of salty water, and the current is flowing all the way through their bodies. So big round of applause for my volunteers, please. Thank you very much. Whoa, thank you. You can take your seats now. Thank you very much. So, that shows us that we can conduct electricity. But now I want to move on to something slightly different, but we're going to come back to ions a bit later. We need to remember what we said about ions for later in the show. So now I want to think about something that we seem to take for granted, and that is combustion, burning. And what we do when we burn things is combine them with oxygen. Now there's a fancy chemical term for that. It's called oxidation. And that oxidation, when it was first used, in chemistry, it was used to mean combining with oxygen. And here, what we're doing is we're taking some fuel, which is the candle wax, we're combining it with oxygen, and we're getting some heat and some light, a candle flame. Now, we're also probably aware that there are some things that don't combine with oxygen quite so readily. Do you recognize what this is? It's a nail. It's an iron nail. And so if I put that in my flame, it will get hot, but you notice it's not glowing or burning or anything. It's just getting hot. So that's not burning. That's not oxidizing in my flame. But this flame is oxidizing some stuff nicely. Now, here, here I have some methylated spirits. And what I want to do is see if I can burn a piece of paper with these methylated spirits. Now, I have a very handy sized piece of paper here. Which I am soaking in my methylated spirits. Oh, where's it gone? So soaked in my methylated spirits, and what I'm going to do is set light to it. But the money didn't burn. You saw the flame? Did you see the flame? But the money didn't burn, did it? Now, what's going on there? Well, this isn't pure methylated spirits. This is methylated spirits mixed with water. So I've added 50 milliliters of methylated spirits, 50 milliliters of water. And what happens there is that the water absorbs the energy from the flame to stop the paper getting hot. And we know that water takes a lot of energy to heat up. That's why we should only boil a kettle with as much water as we need every time we boil a kettle. But what's happening here is that is preventing the paper getting to its ignition temperature, the temperature it needs to get to burn. Does anyone know the ignition temperature of paper? You can give me it in an old-fashioned temperature unit if you like. That's a clue there. It's 451 Fahrenheit. Fahrenheit 451 is a famous book about a society where books were burned. And so that's the relevance of the title of that, because that's the ignition temperature you have to get paper to before it burns. Now here I've got some steel, just like my nail. But what I'm going to do with this is set light to it. And you can see this is quite happily burning. This is quite happily, is combining with oxygen, it's oxidizing. So, and that will keep oxidizing until it's all rusted. Let's start it off over here as well. So that's what it's doing essentially, is rusting, but very, very, very quickly, because combining with oxygen. Isn't it good our cars don't do this? Because you wouldn't get them from the factory before they're all rusted. I'll let that burn the plastic there. Now, it's at this point of the show where I normally stop and I have a bit of a drink. And someone recommended to me to get my energy up for the second half of the show, this stuff, Energade, this nice blue drink. But I've got a bottle of Energade here, and something's happened to it. Now what I need to do is get that blue colour back. Has anyone got any suggestions? Oh, it's back! Now, what's happening here is I'm using the oxygen up here to oxidize, to combine with oxygen, to oxidize the dye that makes it blue. You'll notice it's going back to the yellow color because there's something in there that's doing the opposite of oxidation. There's always, when you have an oxidation going on, so combining with oxygen or something like that, there's always something else going on called reduction. So these are always there. Oxidation and reduction go hand in hand. And they're so common, or they never occur apart. So we call these redox reactions. Redox is reduction at the start, oxidation at the end, redox. And I can do it again. So every time this dye gets reduced by the glucose to its yellow form, it will go yellow, and then every time I re-oxidize it using the oxygen in here, it will go back to blue. And it will keep going until I've used up all the glucose, which is in here for energy, or all the oxygen, which is in here. If I use up all the oxygen, it will go yellow and stay yellow. If I use up all the glucose, it will go blue and stay blue. Now, there was a suggestion from the front, said, "Drink it, sir." Well, if I did that, I would die a very painful death in front of you, all right? Because I have added something to this which is really, really nasty. So don't try and drink this, even if you do it for your friends. What you need to add to it is caustic soda, sodium hydroxide, which is very, very bad to drink. That's why I've put in big letters here, "Do not drink," so that if anyone does that, they would see, "Do not drink." But I'm going to have a drink, and what I'd like to do is I'll invite this young gentleman to open the bottle for me. Would you open that bottle, please? Okay. So can you just confirm to everyone, was the bottle sealed? It was sealed, okay, but you had to break the seal to get the bottle open, didn't you? Yes, he says yes. Trust me, he does. You all heard him say yes, didn't you? So, okay, this is the people's panel here. So I can drink this water. But the thing is, if you have friends round, they might think water is boring. They might like some juice. So you might want to offer them apple juice instead. And so you do that. And then you've got some nice apple juice ready for them to drink. But of course, not everyone likes apple juice. They might say, "I prefer Coca-Cola." So you do this. Do this and make your Coca-Cola, or if they don't like Coca-Cola, you could probably turn it back into something that looks like, so I don't know, some nectar or juice or something like that with a little bit of time. You know. Alternatively, you might want a berry juice, something that's nice dark berry juice colored, but I find that those tend to be a little sour. So what I'm going to do is add some sweetener to this. And this is not very sweet, but it's glucose again. You notice I'm using glucose a lot today. I put some glucose in, and let's see what the glucose does to that. As the glucose dissolves from the bottom, you'll see that the color is slowly changing, I hope, to a nice cocktail, perhaps, a Grahamstown sunrise. So there we are, nice Grahamstown sunrise for me for later. But again, what I'm doing here, as I said at the beginning, is nothing that you cannot do at home. Okay, these are not fancy chemicals. You will have to go to the pharmacy and buy one or two things, but that's all. So the first one, I didn't have anything in here that was actually apple juice. It was iodine, which makes it look like apple juice because it's a sort of yellow color. And if I dissolve some iodine in there, you can see it's a yellow. See that yellow color? Of course, I suggested to you that it was apple juice. There are other yellowy solutions that you might find in various places. To make it into Coca-Cola, we take this and we simply take some starch. That's our maizena that we've boiled up with some water. We take some starch and give that a squirt of starch. We find, so in the second glass, I had a few drops of starch solution. It goes sufficiently black, again, with a bit of suggestion. You can think that that's Coca-Cola. And then the next bit is, we've been talking about reduction and oxidation. The next bit is where we get the reduction and oxidation, where we have the vitamin C. And what that does is to reduce the vitamin C gets oxidized, the iodine gets reduced. Oh, let's just tip some in. And what you see is that black color disappears. Now, this final one was a bit different. This was potassium permanganate. Potassium permanganate is a deep, deep blue, deep purple color when you dissolve it in water, but it's a very, very, very powerful oxidizer. And what I'm going to do here is, oh look, I've got just enough. I've got a little pile of potassium permanganate. I'm going to make a little well in the middle. And what I'd like to do now is a little oxidation reaction. Again, this is burning, but now the oxidizing power isn't necessarily coming from the atmosphere, it's coming from the potassium permanganate itself. What I've put inside there is just a little glycerine. Now, chemistry is often a matter of time, and some reactions take a little while to get going. Says he desperately padding out while this decides to get going. But when it does, you might see a slight change on the top of that tin. Usually it gets going about now. And when it does, you'll see the oxidizing power of potassium permanganate. There we go. It's just starting. So I've mentioned redox. We've mentioned these reactions, reductions and oxidations that go hand in hand. And you may not be aware, but redox is really important for modern day living, because redox is what drives all of the batteries that we use. Every single one of the batteries is using a reduction and oxidation to push those electrons through our mobile phones, through our torches, through our video cameras. Anything that runs on battery power relies on this effect. So what I want to do now is make a human battery if I can. So I need 2 volunteers. So I'm going to choose someone who hasn't got their hand up. Now, I need someone who's got a lot of energy, so that... No. No, the chap behind you, the young chap coming down, the young lad coming down the stairs. And I think I'm going to choose you. It's all right, if you'd like to stand there, and your name is? Jordan. That's a nice, easy name. Thank you, Jordan. And if you'd like to come and stand over here, and your name is? Emily. Oh, wonderful. Right, Jordan. What I'm going to do is give you these 2. If you'd like to just hold them like that. Yeah. And Emily, I'm going to give you these 2 if you'd like to hold those. Right. Now, I'm going to turn my device here into a voltmeter now. No longer does it measure conductivity. It should measure a number of volts. So here I have a battery. It's a well-known black and gold battery. Other brands are available, of course. And you can see that when I touch my electrodes on the battery, we get this many lights. So that's equivalent to 1.5 volts worth. Okay? So what I'm going to do is connect Jordan up, and we're going to see how much energy Jordan can produce. And, okay, 1, 2, 3, ta-da! Oh. I know, just swap your hands around. So, yeah. And? No? Okay, you just keep hold of that. Let's go and see if Emily has got any energy that we can detect. And 1, 2, 3. So, now, I tend to find teamwork works really well. And so what we're going to try to do is see if you can give Jordan a jump start, all right? You look as though you've got lots of energy here, lots of volts, so can you spare some for Jordan? So I'm just going to hook you up like this. This one needs to go here, I think. Oh, fantastic. Can you feel it tingling? No? Oh, can you give him a bit more, please? Just. Can you feel it tingling? No. Oh, well, maybe he doesn't feel it tingling. But what we're going to do, if we check that Jordan has actually got some energy now. Can we do that? Oh, wonderful! You've got energy too. So, big round of applause for Jordan and Emily. Thank you very much. Thank you, Emily. So there, we were using the same principle of the very, very first battery. One of those rods is made of, or has a zinc coating on it. The other rod is made of copper, and there's enough of other chemistry going on in the middle to make a battery from that. And that's what Volta did when he made the very first battery. He took discs of copper and zinc and piled them up with some stuff, some electrolytes, something conductive in between, and found that you could get this voltage. But we can do chemistry in the other direction as well. We can take an electric current and we can pass it through a liquid that passes electric current, and we can do chemistry. So what I've got here is a solution. You can see that it is a sort of blue solution, bluey-green solution. And what I've done is simply taken these two copper rods and I've put them in some water. Now, water we saw didn't conduct electricity very well, so I've added some Epsom salts to this. You could use a variety of things, and that would make some nice investigations that you could do at home. And when they dissolve, some of you might just be able to make out that these will go a little cloudy because bubbles are being formed. Yeah, bubbles are being formed. And what's happening is that electricity is doing some reduction and oxidation, and it's making the copper dissolve. So the copper, instead of being those rods, is now this blue stuff in here. And the copper, these copper ions, that's why they're blue and not copper-colored. And it's a good job copper doesn't dissolve, isn't it? Because we use that for pipes. If it dissolved, we'd be in trouble. But it has dissolved here because we've forced it to dissolve by passing an electric current through it. And if you remember what we said right at the beginning, that sodium ion has a cluster of water around it. These copper ions, these bluey copper ions, have a cluster of water around them. But I can replace that water with something else. I can replace it with ammonia. I've got some ammonia solution here. And if we replace the water with ammonia, these ions will change color. And that's just what I've done, is I've pushed the water out of the way because these ammonia molecules like to be closer to the copper than the water does, and so that's what's changed that to lovely blue color. Now, we're reaching the end of the show, but I've still got a few more demonstrations to do, one of which is about speed of reaction. Because chemists need to worry about not only what's going to happen, but how fast it's going to happen. So I have some methylated spirits here, and I've spilled this on the tablecloth a couple of times, and that's why my tablecloth has now suffered and got a couple of holes in. But if I pour some into a little dish, I pour it very carefully so that I don't spill it on the tablecloth. You can see a flame. Now, that flame is just burning where the vapor of the methylated spirits meets the oxygen. We're not burning the liquid. It has to evaporate, it has to form a gas, and then it will burn with this flame. So that says to me, I could make that go quicker if I could get it into the gas more quickly. So if I use this, now here I've just got methylated spirits in here, and what I can make is a mist of tiny droplets of methylated spirits, and that, you can see, is burning a lot more quickly, and the front row can probably feel it's quite warm. Yeah? Now, that suggests to me that it might go even better if I start with just vapor. Rather than little droplets of liquid, if I start with just vapor. So here I have a bottle. It's just a standard Coke bottle. And what I want to do is ignite the vapor inside the bottle and see what happens. So here I have my little igniting machine. And the bottle just slides over the top there, and I can press this button and we'll see what happens. Now, the secret of science is that results must be reproducible. So we can try that one again. And after three. So, now I did this at home. My wife banned me from doing it indoors for some reason. And I went outside to do it one evening, and it was very cold, and all the vapor had actually condensed. And so it was no longer a gas, and so it didn't do this. So finally, some people say that no science show is complete without a hydrogen balloon explosion. I say it's not complete without a flaming custard demonstration. So I'm trying to get my flamethrower alight. There we go. And so what we're doing here is, again, making sure that everything is well mixed with the air. We've got tiny particles of, this is just maizena. So thank you very much, ladies and gentlemen.